Sunday morning. Welcome to the folk who are here for the first time, and welcome back for those who've been here yesterday. I think we can promise you a very interesting session today with a variety of very different things to attend to. The first up this morning, we're very pleased to welcome Martin Ling, M0LNG, and he'll be talking to us a little bit more about some interesting developments for the future of transponders. Now, we've been very kind of used to the old bent pipe type transponders that would regurgitate whatever uplink signal we could manage and regurgitate it back down on a different frequency. But that need not be the nature of the future, and we'll be finding out a little bit more about that through there. It's an interesting concept, and one that I think we can look to interesting to develop over the coming years. So that's where we're starting from. After that, after our coffee break, will be Ian Young will be taking us into a few degrees of automation in terms of how can we follow all our little satellites and various other features at APRS and various other features that our satellites offer us, but on an automated basis. And after lunch, we might have a treat. We're not quite sure about what might be happening, but we could be following a SpaceX launch live on air if they choose to go. There's always a big doubt on that. But if that gets scrubbed for whatever reason, we'll be looking forward to hearing Heather Nichols give us a bit of a chat about high altitude ballooning. So in the mix of things here, we've got quite a variety of different things to offer for today. So without any more ado, can I welcome Martin to come along and give us a quick talk about your interesting developments.
Okay. Can you hear me? Okay, good morning. So I'm going to go through how on earth I ended up here giving a talk in the hangover slot at the AMSAT-UK Colloquium, why I might want us to have SDR transponders and some things we might do with them, a little bit about what I'm trying to do in terms of adapting that concept to FunCube, and then some sort of next steps in hardware development. I didn't really start out as a radio ham. I know many of you decades of experience on the air. But my background was in sort of R&D projects, first in academia, then commercial things, doing electronics, firmware, bit of signal analysis, model fitting, that kind of thing, and then manufacturing. Ended up having to solve EMC problems, but didn't really have a radio background. And when I did come into that, I found myself more interested in the design and the equipment than in actually sort of talking on the air, so you probably won't have heard my call sign kicking around that much. During sort of COVID period, I sort of needed a side project to occupy myself, and a friend of mine had been, showing off making satellite contact in the park with a handheld and a Yagi that he'd built, and I thought this looks quite interesting. I should have a go at it, and then I'll try the hardest possible way to do it, which is I'll design an SDR to do it, rather because I started looking at what was available in terms of equipment, especially radios that could do full duplex. And there's fewer and fewer things available. So I worked on this design, which was a 2 meter and 70 centimeter front end to go in front of an SDR design that my friend Mike had built called Amalthea, which was based on this Atmel 886 RF215 chip. That's a 2.4 gig and sort of sub 1 gig dual band part. And I was still sort of fiddling that design when I came to EMF in 2022, met the AMSAT-UK team who were there. And then Graham invited me to come and give a talk and then participate in the FunCube group, and then I ended up at last year's Colloquium. And so there's been a sort of process of figuring out, what I might be able to do to sort of help with any of these projects. And so a lot of sort of back and forth with some very patient folk on the FunCube team, dealing with a couple of years of me showing up on calls and asking silly questions and having silly ideas. At last year's Colloquium, we've Frank Zeppenfeld's talk. He was talking about the ESA proposal to do a new GEO payload for amateur radio. And one of these sort of questions that came up in the sort of questions he was putting to the community about what do people want was, do we want analog, do we want digital, or do we want an SDR in space? And this led to some debate in discussions that followed, and a lot of folks seem to feel that these were sort of mutually exclusive things, and if we went for some of the newer options, then we would lose the benefits of the good old bent pipes that we are familiar with. And I ended up sort of in response to this writing this article called Beyond the Bent Pipe, which came out in Oscar News last December, sort of advocating for a sort of mixed approach to this. That ended up included in the AMSAT-UK proposal to ESA, and AMSAT-DL, when they put their proposal in, have similar ideas about doing something a bit beyond a bent pipe. So when I talk about SDR transponders, I'm not advocating for we replace everything that we used to do with that. I'm advocating about we do both, right? So, and to the greatest extent possible, we reuse designs that we already know work. So a pure SDR transponder would be something of the sort where you replace the IF stage in a conventional sort of bent pipe linear transponder with conversion down to baseband, ADC, some processing and software, DAC out to a up conversion out to the downlink frequency. You know, I'm talking about having both available essentially in part of the same transponder, operating in sort of different sub-bands within the uplink and downlink. And there's a lot of interesting properties about this in that, you know, the uplink and downlink can be now asymmetric in that you can have a wider range of frequencies that you're listening for signals coming up in, even if you've got a narrow downlink, and you can be combining different things coming down. You can be having the SDR listen in for stuff that's coming up on the linear transponder bandwidth and picking out things of interest and maybe adding them to the telemetry or things like that. There's a lot of combinations you could do. So in terms of sort of different scenarios that you might want to use this for to do new things, one of them I talked about in that paper was effectively regeneration, right? So you have the satellite detect, demodulate, and decode a signal that's coming up. And then rather than just retransmitting the analog signal that it received, regenerate that in the same form and send it down, but now your sort of SNR is reset and you get the benefits of coding gain on the way up and coding gain on the way down. And if you're in a situation where your link budget is marginal on one side or the other, then that may let you make contact when you couldn't before. The other thing you can do quite easily, because the satellite's decoded the signal, it has to do is store what it decoded, not the whole waveform, is sort of store and forward, which obviously this is not a new idea either. This has been done back to the old AX25 days. But not necessarily storing and forwarding quite some time later or over a different part of the orbit, but even just things like making the communication half duplex. So you transmit up with your handheld, and rather than needing another handheld or a second radio to listen for yourself on the downlink, the satellite would just wait till you're finished transmitting and then echo your signal back down to you. And that makes it easier for people to do things with cheap, crappy radios, which is how we help people get into the hobby. Another thing we can do is cross mode. So you transmit up in one mode on one band, and when that message is transmitted down on the downlink, it could be in a different mode, maybe something that's more appropriate to the other band, right? Especially if we're talking about doing stuff in VHF, UHF, L-band, microwave stuff, it doesn't necessarily make sense to use the same modulations and encodings on both sides of the link. We can also do aggregation, right? So one digital transponder that's been up recently is the Green Cube one, and a problem that you may have run into if you tried to use that was that there was effectively a queue of people trying to get into it all on the same frequency. But if you've got a software-defined receiver listening to a sort of range of bandwidth around the uplink frequency, you can potentially have multiple transmissions coming up at the same time. The satellite can aggregate those messages together and transmit all of them in one downlink signal. That can help. One of the big benefits of all of this is it can help the power budget on the satellite. If you look at what FunCube 1 is doing right now, it's got telemetry running, it's got the linear transponder running, and most of the time it's spending a lot of power running the PA just to transmit a noise floor on the linear transponder. So if we can make the satellite able to identify when there is a signal coming up, when there is actually anything worth transmitting back down, we can turn that PA off, when we don't need it. Or we can, turn down the noise floor on the linear transponder or different things like that. And, so some power spent on doing signal processing in software, may pay for itself in terms of saving power that we would otherwise have spent on the PA from the satellite's power budget. Other sorts of things we might be able to do is listening for things that maybe aren't necessarily directed specifically to the satellite, looking for beacons, maybe balloons like Heather's going to talk about possibly later. Right now, those balloon payloads are generally using APRS on 2 meters, so wouldn't be compatible with like the FunCube 70 centimeter uplink, but it's the sort of thing that can be done, and there's a lot of potential for sort of newer, weak signal, heavily coded modes to be used as beacons and have satellites look for them and report which ones they've seen in their telemetry downlinks. Another part of the sort of ideas I'm exploring here is, slides got a bit messed up, but one of the constraints with doing things in software is you may want to update that software, right? The benefit of doing things in software-defined radio is you can go and change the function of the thing, but how do you do that when the device is in orbit? You need a way to upload new code to it, and if you're thinking about CubeSats and so on, then your bandwidth and your ability to send new code to it is quite limited. But we have the advantage in the amateur community of a whole network of people with ground stations, and so we can potentially do things like the entire time the satellite's going around its orbit, anybody who is interested in that satellite and doing something like running the FunCube dashboard to receive data from it could also be sending data back up to it. And so you can distribute the work of uploading new code that you want to deploy to the satellite as part of that. There's a lot of work you need to do to ensure the sort of integrity and the authenticity of that data, but that is all relatively straightforward to do in software. So when this conversation started in the concept of the ESA GEO proposal, it was about doing SDR in what's probably a fairly large satellite payload, something along the lines of what's on QO100, which, obviously there's a fair bit of power behind that transponder on a fairly big satellite. So in that kind of environment, you could probably put some sort of Linux-based computer on there. You may even be able to have a GPU for offloading some of the heavy computation work. And the result would be something that is fairly easy for amateurs on the ground to develop software for, contribute programs that could be submitted for evaluation and maybe being deployed into space. And in that kind of payload, hopefully you'd have enough bandwidth in the sort of control channels to the satellite to manage that and be able to send updates to it and so on. That would all be quite exciting. It would be a great thing to have. But what about doing it on a CubeSat? And that adds a whole lot more constraints. Obviously, primarily the power budget. Also, physically how much board area you have to put those components on. Another aspect there is heat dissipation. You run CPUs, they get quite hot. Even if you can handle the power consumption, you can't necessarily dissipate the heat. So you're going to be constrained to a lot less computational power to do anything with these signals. Your bandwidth and the sizes of sort of messages that you can get up to it in the space of a pass is quite limited. And you've got to think about how you're going to integrate that into the overall CubeSat design without adding all of unnecessary risk to the mission. So the sorts of solutions that I'm thinking about here is that this would be a microcontroller-based thing, probably with an FPGA for some offload of some of the heavier computation work, which is going to be a much more difficult thing to develop for, at least with how it's been done more traditionally. There's some things in the pipeline in the software world that may make that easier. It needs to be to a very limited bandwidth because we just won't have the computational power to crunch more, sample rate than that. It would need to be, effectively a sort of a payload on the satellite that is sort of, completely under the control of the main command and control system on the satellite. We can't rely on the main control system link for updates, so it would need to have the code on it to receive its own updates and decode them and so on itself. You want to minimize the amount of code you have to send to it. So you'd be splitting that code into different regions and try and reuse modules. So you have a bit of code that does an FFT and you don't change that. You upload different things that use it in different ways. And obviously you need ways to make sure that anything you do upload to it is what was intended and authorized to be uploaded. So you have crypto hashes and signing keys and so forth. There are some projects around trying to do things like this. Back in December, I met some of the LibreSpace folks at the CCC Congress in Hamburg, and they had one of these boards with them. This is the SatNogs Comms board. And actually, this is interestingly similar to the thing I showed you at the very start of the talk. It's got that same Atmel chip in it. So it's L-band and UHF, sorry, S-band and UHF radio with a microcontroller, an FPGA. They're sort of targeting this, to be the sort of main communication system for a satellite with fairly wide bandwidth and high link speeds, I think up to 1 megabit per second a data rate on S-band. So this is a fairly power heavy design. I think this is up to 8 watts in transmit. So this is not the sort of thing I'm talking about here, but it's another example of trying to do SDR in a CubeSat form factor. So what I've been looking at is how could we sort of retrofit a sort of minimal version of this into essentially the FunCube design for targeting FunCube Next, the 2U mission. So this is a block diagram of the RF board that's up on FunCube 1 right now. And if I pull up the, put it on its side, the diagram of the sort of overall architecture that, aiming for here, we already have some of the elements here in that you've got your uplink coming in through here, going through a couple of down conversions. So you've got a 10.7 meg IF stage here, where it splits to 2 branches, one to the linear transponder, one to the FM receiver. That's part of the command and control. And so that is the point at which we'd want to, tap off it. And then for a downlink, we'd want to tap in down somewhere like here, where we're taking, the telemetry feed, the linear transponder feed, and combining them. So this is an idea that fits quite closely into what is already happening in the FunCube design. There's some questions about exactly where you tap, like do you go after that crystal filter, or do you have a slightly different crystal filter to have a different bandwidth for the SDR subsystem than you do for the linear transponder? And do you come out at the IF stage before this mixer, or do you come out at the RF stage after that mixer? David's recommendation was that we look at the coming out at RF. So this is a sort of block diagram of what my sort of proposed approach at the moment is. So you come in at 10.7 megahertz. So you've already had the benefit of the 2 down conversions, the IF amps, all the filtering that was around those. So you've got a pretty tight, clean, you know, maybe 20, 30 megahertz, 20, 30 kilohertz of bandwidth at this IF frequency. We're now basically building an HF receiver, right? A very popular way to do that is with Dan Taylor's style of according to a sample detector, which takes you straight to baseband INQ. And then there's a number of designs out there that then use ADCs that are essentially designed for audio applications. So have, you know, typically 48 kilohertz of bandwidth. So this is if you've looked at an MCHF or any of the designs like that, that kind of thing. And the digital side of that is an I2S bus, which is a serial bus specifically for transferring digital audio, sort of within designs. The DAC is the sort of inverse of that to the TX side, and the idea we have at the moment is to use one of these Linear Tech 5599 chips, which is a direct IQ modulator that would take that baseband straight up to 145-ish meg to go into be combined towards the PA. On the processing side, this would be a microcontroller, probably something like the STM32. The higher end ones of those, like the F7 or H7 series, which you can clock at a couple of hundred megahertz. And that sort of thing is already able to do quite a bit on its own. There's been some demos of doing FT8 decoding on a, I think, STM32 F7, not with the same, you know, level of success as, you know, what you can do on a PC, but still able to do some quite significant work. And I want to pair that with an FPGA, a small, low power one, ICE40 from Lattice, which gives us a way to take, you know, certain tasks that are expensive, like the LDPC decoding for some of the digital modes, and move that into digital logic, so with some RAM attached. And so from the point of view of the rest of the satellite, this is just another thing that we control over I2C and have a switch that turns it on and off, right? And the control will be very simple, like run program 1, run program 2, run program 3, or turn off, you know. So we're not adding complexity to the management of the satellite, but within those programs, this could be doing things like receiving a new program that's being sent up from the ground. So you have effectively a sort of bootloader program that could be selected, that can, when it's fully transferred, then be run on this. I've been working on sort of trying to flesh that design out. And one of the questions in doing that I ran into was, what's the power level at this point? And it turns out that's quite a good question, because, well, we know the gain of all this, but, you know, when the thing's actually in the space, how much power do we actually see at the antenna? So what do we know? So when Funky Bomb was being tested on the ground, you know, sort of confirmed that you could get into it with a signal at about minus 115 dBm in SSB bandwidth at the antenna. But if we're trying to do things in the SDR where we're trying to sort of pull signals out with lots of coding gain from almost under the noise floor, we might be interested in, you know, looking at signals that are quite a bit below that. So we might want to look down to maybe 135 dBm or even below. We know that the the gain control kicks in when the signal at the antenna gets to about -90 dBm, but that gain control is here in the linear transponder. So that is after we'd be talking about tapping it off. So we wouldn't have the benefit of that AGC, and in fact, I don't see that AGC as a benefit. If you're trying to demodulate signals digitally, anything that's sort of messing with the signal level is just an extra variable that you have to account for. Much better to have the dynamic range to see the whole thing. So I was doing a bit of research on, what sort of signal level might we see in space, and it turns out people have looked at this and tried to map it out. So this is from a paper that came out a couple of years ago, looking at radio interference in the 70 centimeter band from the SERPENS satellite. So they collected sort of signal strength data over the course of a lot of orbits, I think over 2015, 2016, and mapped it out. And, I haven't managed to do the math to figure out exactly how these signal levels might map to what you'd expect to see on Funky. We'd have to account for all the differences in their signal path and ours, and the different antenna types and so on. But it might be kind of broadly in the same ballpark in the sense that, in quiet areas, if we can find we can get in at -115, well, yeah, we're above that noise floor by a few dB. But you see the worst case spots of this, and it's a bit more obvious in this other plot, are quite a number of dBs above that. And this satellite they were measuring it on wasn't going up, didn't have enough inclination to be going up to the latitudes where it actually gets even worse. We're in this situation where we might be wanting to look at signals from sort of down here somewhere, whilst there's noise up here somewhere, possibly, right next to it. So we do want quite a lot of dynamic range in this thing. There probably is quite a lot of analog dynamic range at that stage of the signal path, because this is before all the gain in the linear transponder. So I've been working on that receiver design. It looks something like this. So you've got a 50 ohm input. This would be on a little coax feed from the RF board, coming into transformer to a differential. You've got your quadrature sample detector. So this is switching 4 phases of a clock to sample the signal at different points, and you end up with differential signals coming out that your I and Q. We have some gain here because even at the sort of top end of the expected range, we're likely to be a bit short of what you need to sort of fill the ADC range. You also fit some filtering into that as well, so you're helping take the edges off anything that's strong that might be sort of just outside the IF filter. The idea with this is to bring that sort of 20 kilohertz of bandwidth, not all the way down to DC, but offset by a bit, because if you've worked with any quadrature sampling SDR receiver, you'll know there's a spike in the middle where you've got the LO bleed through, you've got the DC offset. You don't want that right in the middle of your passband. So the thinking here is we might have this sampling at, say, 48 kilohertz. So you'd filter this down to maybe 30 kilohertz, and you have your LO frequency for this sampling detector offset by 12. So at DC you have, a baseband, you have the sort of signal of interest sitting here, and it's been through the IF filter that's there and this filter, and then you've got this out the way, which also means that the LO frequency from this and its harmonics aren't interfering with the other stuff that cares about that LO elsewhere on the satellite. So this is the one part of the design that's basically complete, and the other side, the output side, is really a lot simpler. There's not much complexity to that. We know what signal level we want going into the downlink side. The hard part really is what you do in the middle, right? Now to actually make this do anything, we need to write an awful lot of code. And there's a bit of a sort of chicken and egg problem here, in that I'm simultaneously trying to design, what the hardware that runs on looks like, exactly how it's put together, how much power it draws, and so on. And unlike analog stuff where you build it, you turn it on, you make sure it works, and you see how much power it draws on the meter. Okay, good, that's fine. With digital, it all depends what you're doing, right? So you can't really see if this is going to do what we want at the power budget we want until you've written all the code to make it do the thing you want. So I'm at the stage at the moment of sort of trying to find what the smoothest path is to being able to develop that. And that's also, not just about making it easy for me, but we want other people to be able to contribute software to this. So, it needs to be something that's tractable to develop. I got stuck on this for a long time. And meanwhile, I was distracted by projects we were doing at work that was taking up a lot of my time. And then eventually I realized, oh no, I can use the work project to fill this gap in the middle. So this is what we've been building at Great Scott Gadgets lately, which is a USB capture and analysis and development tool. And you can be used for various things, but it's got a couple of PMOD ports on it. It's based on an FPGA. It's based on the same FPGA that we're using in some SDR radio projects. And because of the gateway libraries and so on that we've got, I can quite easily take that, make it be a USB audio device, hook it up to GNU Radio, and run the RX side of this into GNU Radio and the TX side of it out of GNU Radio or whatever other software on PC, and work on pushing parts of the processing pipeline into the FPGA, which is another topic we've been sort of looking at in terms of how do we make that easier, like up to the point, some work my colleague Mike did, which is about, you have your blocks in GNU Radio, you have your FPGA-based SDR connected, and you literally just push the blocks into the FPGA. And there is some of that working, although it needs a lot more work. That's also a direction that I think the GNU Radio folks are sort of moving towards with some of the GNU Radio 4 architecture. So it's going to become easier to do things like that. And there is an increasing amount of stuff being done now for signal processing on FPGAs and FPGAs with the open tool chains. Many of you know Daniel Estevez and the Maya SDR thing that he's done for the Pluto. That's all written in Amaranth, which is the same Python-based hardware description language that we're using in these kinds of projects. So, okay, that's kind of how I'm approaching this. What sort of things might we want to implement with it? Well, the requests I have from the FunCube team at the moment are dead simple BPSK at 1200 or higher baud rates. That's sort of our baseline thing we might want to do as your sort of fail-safe, probably the most basic way of uploading software and configuration changes to something like this as well, with something based on that. And in terms of doing that on SDR, it would be not just about, find, demodulate and decode that, but do so when there's other strong signals in the passband. Can you still find the interesting BPSK thing down here when there's a big bit of noise here? Can you find multiple ones at once? Can you do those in parallel, that sort of thing? The other thing that people are keen on is weak signal modes like FT8, FT4. FT4 is a bit more preferable for satellite work because of the faster conversations. These are quite tricky to do on LEO sats because they're very sensitive to Doppler shift. If you look at an FT8 signal, it's 8 FSK, you've got eight little tones. that signal is made up of, and they're 6.25 hertz apart. And it's not so much the Doppler shift, but the rate of change of the Doppler shift, the slope on the waterfall, is what makes these difficult to deal with. And even if you're sort of compensating for that with tracking and so on, if your clock is off by a bit, if your TLEs are off by a bit, even that can be enough to mess it up. So something I'm looking at is, can we put the necessary intelligence in the satellite side to have it figure out the Doppler and decode this with those effects included? Another question is, is that a right approach, or is there the opportunity to do something new here that's actually sort of optimized for the LEO QSO case? Something that's designed for robustness against Doppler, maybe PSK or MSK based rather than FSK, so that it's easier to track what the overall sort of curve of a signal is. I've got some ideas about how we might sort of lock to that efficiently by having a preamble that sort of chirps at different slopes, and you look for something straight, and that tells you both that you've found something and also which part of the chirp it was by the fact that it's straight. If that's the sort of topic you're interested in, there's a couple of pages that are well worth reading. One is, again, Danny Estevez a few years ago worked on testing FTA and modelling the Doppler issues with it. So that's a good thing to read. And this page here about implementing a basic version of FTA in Python with NumPy and so on is a really good read if you're interested in how this works, because it's quite clever. It's a very direct mapping of the sort of FFT to the decoding process, and like a bin is a pixel, you're almost sort of pointing a barcode reader at it and just trying to take it out. But the hard part with these sorts of decoding things is finding where you need to look with the decoder in the first place. You've got to find these signals by having some quick way to spot them. In FT8 it works with looking for these particular patterns that show up at the start and the end of the signal. And when you find a pair of those, you go, okay, I'll run the decoder on what's in the middle. But that's obviously not going to work when the thing's slanted, when the thing's curved, and so on. So it's things like how do you adapt that? And also if we want to sort of remove the need to do the Doppler collection from the ground, and we're doing this over a 20 kilohertz bandwidth, you're now looking over almost 10 times as much bandwidth as when you do it on SSB. Yeah. So that's kind of where I'm at with it, and very happy to take any questions. Yeah.
Instead of FT8,
Yes.
everyone just use. I'm sorry.
Start again. Instead of FT8 and FT4, which everyone uses just because it's the most popular flavour of the month,
Yes.
the old JT9
Right.
that seems to have got ignored has got some fast modes associated with it.
Yes.
50, 100, 200 baud, burst modes. Now, I've used them through QO100 and they're absolutely wonderful.
Right. Yeah.
For the uplink.
Yeah.
They're burst modes, short bursts, so you can transmit different messages in the same transmission if you want.
Yeah.
And WSJT, it's all built, it's all there in the software that everyone's got.
Yeah. So that would be an option.
Furthermore, it's convolutionally encoded, so you can use a simple Viterbi decoder in the satellite. Far simpler than trying to do FT8.
Yeah. No, I'm totally open to that sort of thing. I mean, I also had a look at MSK 144, which is the meteor scatter mode, because that's obviously designed for very short bursts, and in a short burst you don't care so much about any of the Doppler effects.
I've tried it on QO1. My link project won't work with 144.
Right. Okay. Yeah. Yeah.
Any more? Okay. Well, sorry.
What sort of timescale are you envisaging?
What sort of timescale am I envisaging?
Is it?
I'm not committing to anything.
Okay.
You know, in theory, this is aimed at FunCube Next, which is in the process of moving to the right, as these things do. But I am absolutely not committing to having anything, built. If I do, great. If I don't, it doesn't. I'm not taking that risk.
One question. Sorry, question from Peter on the stream.
Yeah.
Will others be able to contribute and participate? Are you planning to release it as open source hardware and software?
Yes, absolutely. I'm fully about open source. All my stuff is open source. I don't have those schematics up yet, but I'm happy to make those available. And yeah, if there's people who want to collaborate on this, I'd be very happy to talk to them. I'd love to have more people to work with on this. This is not something I'm precious about. It's not necessarily something I want to do by myself. It's something I've been doing by myself up to now because I'm the only one doing it.
Nope. Okay, well, thank you very much, Martin. It's been quite a substantially deep dive into some very interesting and new technologies, which I think are going to be very exciting to see how this all pans out in the future. Challenges, certainly, but it's certainly a whole new field of development that I think it's one of a hobby that we've got that allows us to sort of progress into all these new technologies in time and so on. So thank you very much indeed. Thank you. So I guess now coffee time, just about, and we'll reconvene in about 30 minutes with Ian, and so do come back for the next exciting installment. Right, welcome. Welcome to the second session, and we're pleased to have Ian, who's no stranger to us, to these presentations, and so it's carrying on a theme of developing new ways of tracking satellites, new ways of receiving telemetry, new ways of using our opportunities in space to explore all sorts of new features. So without much more, I don't think Ian really needs much introduction. We've known him for many years, and so over to you, Ian. Tell us all about it.
Okay, right. This presentation is strongly based off one I did in 2018, but has been updated to remove some obsolete material, and there is some new material that I added. So I'm going to cover automating the reception of PhoneCube, telemetry, weather satellite pictures using GNU Radio. Okay, we'll do it the old-fashioned way. So, as I said, we're going to cover station software and hardware. We're going to cover how you receive PhoneCube, how you would receive APRS packets, mainly from the ISS, and how we would recover weather satellite pictures. And then we'll have a quick wrap-up at the end. So, for the hardware, PhoneCube antenna, a turnstile, a wideband amplifier, a splitter. Now, what do we use the splitter for? To feed an extra pi from the same antenna, so we can do two things at once. PhoneCube Dongle Pro Plus is the hardware, although you could use a RTL dongle as well. Raspberry Pi 3, it's only a 3. GNU Radio for the software, and AMSAT PhoneCube telemetry decoder. So, how do we go about receiving the PhoneCube satellite? Well, in the digital world, you still have to do exactly the same thing as you do in the analog world. First thing is you've got to acquire the signal. Then you've got to tune it, filter it. Since we're talking about telemetry here, this thing got to be formatted, decoded, and then, if you wish, uploaded to the data warehouse. So how do we do all these things? How do we acquire the signal? In GNU Radio, we have a concept called blocks. And in this case, we have a specific block that allows GNU Radio to talk to the PhoneCube Dongle Pro Plus. It has a bandwidth of 192 kilohertz. If we tune to 145.9, we get all of the 2 meter subband except 4 kilohertz at the very top. So pretty much the whole thing. Now we've acquired it, we need to tune it. How do we do this in GNU Radio? There is a block called a frequency translating fur filter. Now, a lot of you might not know what that is. I know you do, Martin, and I know Heather does. See it as the big fat tuning knob in the middle of your rig. That's a very simplistic way to put it, but it's also the simplest. Okay? And then, so that will then tune it to the beacon frequency. If you notice, the center frequency is not an absolute frequency. It is an offset within the 192 kilohertz. So that is one big difference between the digital world and the analog world when you're dealing it in baseband. Also shown on screen is a rational resampler. I will explain a bit more about that later on, but effectively what we do is divide it down so that we don't have so much bandwidth to process later. Now, since we have Doppler, we have to deal with it. Luckily, GNU Radio has a block that allows us to control the flow graph, as we call it, remotely. So I wrote a script that once a second calculates the Doppler shift by talking to a satellite protection program. I actually use predict. That sends the information to the flow graph. And then it adjusts for Doppler. This lets us get more telemetry packets down. And you get a nice straight line on the waterfall rather than a wavy one. Or sloping one, I should say. Now, we're actually ready to filter and resample. Yeah, we want to filter it so that we've got the largest signal to noise within the filter possible. But we also need to resample it down to 96 kilohertz, because that's what Alex's decoder requires. So we resample it, it's the same resampler you saw on a previous slide, and we pass that through a low pass filter. I chose about 4K bandwidth because I found that was the most useful from a computational perspective, but also takes account of any residual Doppler and also gives us the largest signal to noise ratio while still, permitting the beacon within the bandpass. So we've now got our nice clean signal of 4 kilohertz bandwidth. The decoder also, so we've now got to format the signal properly for the decoder. The decoder requires the signal to be mixed in with a 5 kilohertz signal to shift it up 5 kilohertz in the spectrum. It also requires the data in a particular format, so I'm not going to go too much into this on this slide, but essentially we mix in a 5 kilohertz signal to shift it up 5 kilohertz. We multiply it by 48K, and then we change it to a different digital format and then send it on to the decoders themselves. Yeah, I'm not going to get too much into that because that's all very geeky and techy. We're at this point here, where these yellow connectors are, we are well and truly out of the RF spectrum and into the computational world. Here is the entire signal chain. And as you can see, it's actually not that many blocks. So I just left that one in for completion. Yeah, this software is available. Like Martin, I'm all for open source. So if anybody wants a hand, this was built with a GUI anyway. So you can actually install the new radio, take these slides and create your own. Yeah. Just a little bit on Alex's decoder. It listens to a UDP port. So you need a little bit more Unix plumbing. Two utilities you can use there, SOCAT or NetCat. It decodes the telemetry packets, boo, and then pipes into a shell script that uploads them to the FunQ warehouse. Yeah, there is a newer development here, and this is part of the slides here have been updated. There's a decoder built into geosatellites, which is better, and Alex will tell you that himself, which helps simplify some of the signal chain, because you don't have to do all those digital conversions I spoke. Now, what if we want multiple receivers? Well, whereas using an analog splitter can be done, as we all know, that's a 3 dB signal loss. However, in the digital world, you can split as many times as you like and not lose any signal once you've acquired it. So here we have the signal acquisition. It's the same block you saw before. But if you note, I send that signal to two separate frequency translating FIR filters, or two big tuning knobs. Yeah? If you look carefully, you'll see they're on different frequencies. So this, back in the day, was allowing me to receive multiple FunQ spacecraft at the same time and just leave it running. So, and obviously not shown here is two rest of the chains. So that's FunQ. Before I go on to the other spacecraft I'm going to talk about, any questions? Because I know it's a lot to take in. Okay. APRS. They're all on the same frequency. So there's only one extra signal chain required. A center frequency of minus 75 kilohertz or 145.9 will get you on the right frequency for the FIR filter. You need a software CNC. There are plenty out there. Direwolf, the old Linux sound modem, and all the rest of them. Direwolf is probably the favorite these days. But we also need a sound card. So how do we do that in GNU Radio? Now, you actually need a linear receiver, yeah? It needs a sound card, as I said, but actually you send audio out to the sound card. So you need a way to get it into your software decoder. So you need a virtual audio cable, or in Linux, you might use Jack-D. So what do we have here? This is the full receive chain for APRS. We've got the FIR filter again. Yeah, we've got a low pass filter. We then have to convert it from an IQ stream to something the sound card could understand. And we call that real. Yeah. We then resample it down to the sample size of the sound card. We multiply it by a constant to get an amplification and send it out to the sound card. On the other side of that sound card, there's the virtual audio cable, which you then connect to your software decoder. So far, on a single Pi 3, decode the entire telemetry from the entire FunQ fleet, however many that are still transmitting telemetry. You can receive APRS packets from the entire APRS fleet. But hang on a minute. Weather satellites aren't too far away, are they? So what about them? They are on a slightly different frequency, but they're within the dongle's frequency range. Tip here, there's little known limitation with the GNU radio FunCube and RTL drivers. Yeah, once you set their frequency at program startup, you can't change it without stopping and restarting. Yeah, so need a second Pi and dongle in order to do weather satellites as well. Now, we are explicitly talking about the weather satellites on 137 megahertz-ish. I'm not going to deal with the stuff up at L-band that needs a steerable dish. Yeah. So there are two main types. The NOAA APT fleet, which has been going for donkey's years, and the Russian Meteor M2.X fleet. I think they're up to 2.3 now. They've had a couple of incidents with a couple of them in different ways. One failed on launch, one went rather loopy on orbit. Again, frequencies are spread across the entire band. It's larger than 192 kilohertz, but the signals themselves are small enough bandwidth to pass through 192 K. So, again, first thing we've got to do is acquire the signal. So, when I designed this, we have a separate flow graph for each spacecraft, because as I said, once you set the frequency, you can't change it. I have a script that runs at midnight, gets all the passes, excludes those that don't get above a certain elevation, because if there's 2-degree pass, it's pointless. Yeah, sets the priorities, and schedules each flow graph to stop and end, so that the next one can then set the frequency appropriately. So, how do we decode it? Well, due to the fact that we've got to stop and start, we essentially record the raw data and then process it later, when later means we've stopped recording. So actually, what I actually did was the scheduling script takes care of kicking it off anyway. WX2IMG is used for the NOAA spacecraft, but I do have another flow graph, again from Alex, that decodes the raw data as well. Quite interesting comparing the two. But what about the M2 satellites? There is a decoder for the Raspberry Pi and one for the AMD Intel chips. It does work, but it will take hours to process the pass. Thankfully, there's only 2 passes a day, one of those is at night. The Pi 5 will be faster, but I've got to get around to swapping that hardware out. It is on the list, but it's on the get around to it list. It got put on there when Pi 5s were in short supply, on account of that was the limiting factor. Now, the limiting factor is everything else that's going on. So, I've just got a couple of pictures to show you here. That is from NOAA, I think it was 19. As you can clearly identify the UK, and Iceland for that matter, and Europe, but there is interference at the top and the bottom, and some nice dark lines in the middle. That spacecraft goes over at about 11 o'clock in the morning. That's when a whole lot of the pages on 137 megahertz start transmitting in Coventry. Your mileage may vary. This one is from Meteor M2, before that one, or M2.2 I should say, before that one broke. Again, you can clearly identify the UK and Europe. This one, you will see a couple of bars at the top. Yeah? They are actually one of the NOAA spacecraft that's on a very similar frequency, causing the signal to drop out because the Meteor spacecraft uses PSK, QPSK to be precise. So of course you either get it or you don't. Yeah. For some reason, they put the Russians put their spacecraft on a frequency very close to the NOAA one. Now this is, believe it or not, the low resolution. You can still identify the Pyrenees and the fact that they've got snow on them. So that kind of tells you what time of year it was. So that's just really to compare the quality of the two. Bear in mind, it's all on the same hardware. You know, that just shows you the difference between the analog transmission and the digital transmission. Other possibilities, some of which I've done, some of which I haven't. With a HF upverter, you could receive the weather facts from Northwood in Germany. You'd want to use FLDigi with that, but yeah, you just connect FLDigi to your virtual, excuse me, virtual audio cable. You can also receive the DAF text messages on 490 kilohertz and 518 kilohertz in a similar manner, and I have done that. Unfortunately, Northwood can be very weak for me, so I didn't really get to that. Okay. Future plans. Well, we heard about 2 potential new FunCube spacecraft, since they all use the same telemetry format. That won't be a problem. When AMSAT-NA get their Golf spacecraft going, depending on the telemetry format picked for that, then there's no reason why we couldn't do that. Obviously, there's adding future Meteor spacecraft. That's definitely on the list. There is one planned. You know, add a third pipe for WeatherFax and Navtex. I don't know what's gone wrong with that slide because that part of using the GSAT decoder was deleted. Upload weather pictures to a web server. I actually already do, I just don't publish it. And the telemetry values could be sent to our RD tool or something else for graphing, but the truth is we've now got one for warehouse, so there probably isn't much point. So, with that, any questions?
Anyone got to fire away? No. Well, I'd certainly opened my eyes to a lot of interesting things that you can do with GNU Radio. I think it's a fascinating tool that allows us to construct digital or pseudo radio components and link them all together in all sorts of different ways. And it's far easier than getting a soldering iron out and trying to design some filters and put some components together. And you know, I think there's it's a toolbox full of all sorts of interesting bits and pieces when you start taking the standard parts of GNU Radio and then adding in the specialist bits that Seth and various other people have written. I think it becomes quite an interesting toolkit that you can then develop all sorts of different radios from.
If I could just add something there. Right, what I would say with GNU Radio, don't try to chew it all at once, take small bites, start easy. You know, all of that was probably 3 to 5 years worth of understanding GNU Radio. Writing those flow graphs, when I came to write them, took me an evening. But it's finding out and understanding the concepts behind it that takes the time. It's a very steep learning curve, but
well, good luck. I mean, that's what we like, isn't it? Steep learning curves and challenges. So, yeah.
Hello, Ian. I wonder, How do you start in learning GNU radio?
That's a good question. Yeah. The first thing, what did I do? I looked around the web, found some examples, and one kind of did what I wanted it to do, and I started fiddling. And then I took it back to first principles. First thing I did was get one of those signal acquisition blocks and connect it to a waterfall. And then I put a filter in and fed that to a separate waterfall. So I work out what it's actually doing. And then I put a resampler in and built it up, built it up, built it up. And so that's how I started, which is actually why I took you through those steps of having the acquisition, then the tuning, then the filtering, then the decoding, because that's exactly how I started and exactly how I built it.
Hi Ian, John, M0IDA.
Hey, John.
Thanks for the presentation. For the willing experimenter, could you just take a step back, please, and describe the initial signal acquisition and what might be a good place to start physically?
Okay. Essentially, SDRs are basically, to simplify it, they're simply big fat ADCs. You can actually use a sound card for VLF stuff. So you will have a dongle which tunes to 2 meters. So you program that dongle to tune to 2 meters, and you get out an IQ stream out of its USB port, and that's how it actually acquires that's how you acquire the signal. What it does in hardware, that's black magic.
Hello, Ian.
Hey,
Yes,
John.
so I was going to say one of the better ways also to learn GNU radio is to possibly not do it on a Pi, because they are a little bit gutless. So people have only got laptops to a penny.
Yeah.
And it's a much more pleasant experience than
that's
resource limited.
Yeah, that's a good point John has just made. The truth is, I didn't develop it on a Pi. I ran them on a Pi. Yeah, I've got a dirty, great big machine that was built for GNU radio with 8 gig of RAM and goodness knows how many CPUs, and so I would develop the flow graph on there, then push it over to the Pi, because it's all written in Python. Of course, as long as you've got the libraries installed, then it will run anyway. So yeah, I would not recommend starting GNU radio on a Pi. Use that for when you want to run something like this autonomously, stuck in the garage once you've actually done the development.
Any more for any more?
You're not allowed to ask questions, are they?
No, I'm not going to ask a question. Just to follow on from your answer about the whoever it was asked about how to do it. Recently, in the last year or two, they've really improved the online examples. There is a lot now of tutorials either built in or in the websites for GNU Radio.
Yeah, I guess I started long enough ago.
So did I, but right from your first SDR right through to doing the actual decodes of some of these satellite stuff in manual mode.
All right, another one.
Hi, as a relative novice complete novice to satellite work, is there any reason you're using an SDR with such a low bandwidth? Like you can get 10 megahertz out.
No, I do have some nice USRP devices. Yeah. I use those for other things. They're doing it in my QL 100 station, for example. Yeah. This was done as a small, self-contained, running 24/7 device, and for what it needed, I didn't need 10 meg. I needed 192 kilohertz. Well, 200 would have been perfect, but yeah, I'm not going to worry about that. And so it was meant to be low power, running 24/7 autonomously, stuffed in the garage, connected to the antenna, and I forget about it. I can go do more interesting things with my time.
Yeah, that makes sense. Thanks.
Yeah.
Yeah, I guess it also reduces the amount of processing power. If you've got 10 megahertz worth of data,
Yeah.
that's a bit of a hard cookie to crumble. And
That's another good point. If you've got 10 megs, that's great. You've got to process it down. And if you're looking for a 4K signal, what's the point?
Good. Any more? Oh, another one.
I was going to say also, it does mean that you choose the SDR. It's appropriate, as you said, Ian. But you can be looking at receivers or transceivers or whatever else you may want to stick on the end there, and as long as the block supported.
Yes.
Right, or you can get it into, say, raw audio or whatever you need. You can just throw it in there, and it gives you and you can basically use most of their, say, the examples shown there by Ian. You use most of those and just change maybe the input or the output block, and you run away. It's
Exactly.
fantastic.
Yeah, and some of this would have been developed on the one of the early USRPs, because that's what I had at the time. But then again, I don't want to waste that running 24/7 when I can buy a dongle.
Any more? For any more? Well, I think it's just to say thank you very much to Ian for a very interesting presentation.
Thank you.
Thank you. Yes, and I think it highlights the technologies that are available to us to experiment and play with constructing and designing our own radio systems from kind of modular bricks and blocks, and then logically just connect them together in a structure.
Yeah, it's get my teeth back in again. It's actually no different to what went on in the analog world when people were building their own oscillators, building their own filters and PAs. It's just what's on the screen now, and you don't your fingers burn with a soldering iron.
Yes, it's the glue is now logical glue rather than solder. Good. Okay, small break now while maybe a bit more, half an hour break or so until our next one. We're setting up a Zoom session, and Peter will be giving us an update on AMSAT-DL and their activities. So take a break, take a pause. We've probably got time for a coffee, and be back here in about half an hour. Okay. Right. We call you to order. It is the allotted time, and we're starting a teleconference call with Peter, who can't be with us in person, but will be telling us all about. We'll make some mention of their recent celebrations of 50 years. So I don't know. Over to Peter.
Yeah, thank you very much. I hope you can hear me.
Yes, I'm hearing you very nicely. Thank you.
That's perfect. So, yeah, you see, this is not a recording. We are in a live session. So, yeah, welcome everyone, and thanks for having me. Yeah, it's. I think there will be some excitement guaranteed today. I guess mainly after my presentation, when everyone is going to look hopefully for the successful Starship launch. Well, in my presentation, I want to give a short flashback to the 50 years we celebrated actually last year. And yeah, I would like to focus, maybe not everyone is aware what AMSAT groups worldwide are doing. And AMSAT North America was indeed founded before AMSAT DL was founded in 1973. I think AMSAT UK is also soon going to celebrate 50 years. I think I would like to put the focus also on what actually AMSAT is. So we are practically a non-profit, non-commercial organization. We are even charitable. And all what we are doing is voluntary work. That means nobody of the traditional, let's say, of the AMSAT organization like AMSAT in North America, AMSAT UK, AMSAT HB, AMSAT France, and others as well. So we are run by volunteers. That means we are not paid in any way for the things we are doing. We are not doing this commercially. And I think that is important to understand. Basically, we do everything in our free time. Usually, we get compensation for projects when we have to do some trips or something like that. So usually those costs are compensated, but we are in no way paid in any way for the things we are doing, for the things we are flying or anything like that. So we completely depend on donations, on support, like AMSAT DL. Now and then we get support from the DLR, for example, if we have an interesting project for them. But that money is always only spent on material, launch costs, and things like that. I think that is important to understand. And also, like AMSAT UK, AMSAT North America, AMSAT DL is a registered organization. That means we have an elected board of directors, which are elected by our membership. So if we, let me see how it switches. Yeah. So if we look back, it's quite a history, starting with Sputnik in 1957, which was not an amateur radio satellite, but which was in practice received by many radio amateurs, and actually the radio amateurs were even the first one to get it. Even in Bochum, Professor Kaminski, the founder of the Sternwarte Bochum, was one of the first to receive Sputnik 1, and that actually made everything possible what we are doing here in as an AMSAT community. So we have Oscar 1 in 1961, and indeed very interesting Oscar 7, which is still alive after so many years. Then as an AMSAT DL group, we were, and AMSAT DL already was founded, as I said, in 73. Some of the transponders built for Oscar 7 were done by AMSAT DL. And if you look at AMSAT DL projects, we have the famous Phase 3A satellites, Oscar 10, Oscar 13, indeed Oscar 40. Then we were in around 2004, we were looking to go to Mars. And finally, in 2018, we got the first geostationary amateur transponder, or a kind of hosted payload on the SHAL-2 satellite from Qatar. And now it's almost 25. The year he has a reason, we will see later on. We are going to build some small satellites, our Arminas mission, which is going to be launched with Rocket Factory 1 rocket in next year. So Martin showed this graphic already yesterday, showing how many satellites were launched. And yeah, you see it's going exponentially up. We even have about 100 Oscars or even more now in orbit. Most of them are with, as soon as they got an Oscar number, then it is clarified that they really contain an amateur radio payload, something like a transponder. So not all of the CubeSats launched or satellites launched in the last couple of years are amateur radio satellite. Also, they are using amateur radio frequency. So sometimes we have to look at that. But fortunately, we also have the IAU frequency coordination, which is taking care. Yeah, so a lot of amateur radio satellites have been launched, as I said. Not all of them are amateur radio. Not all of them are from AMSAT groups, and they are still qualify as an Oscar. For example, satellites from universities, educational institutions, and so on. But sometimes we are also seeing problems with commercial use of our frequencies, and not all satellites using our amateur radio bands are actually satellites carrying amateur radio. Also, they use the frequencies, and most recently there is a constellation of satellites in orbit called Bluebird 1 to 5. These satellites use amateur frequencies, but they are strictly commercial. It's a little kind of a problem. I have extracted here the FCC paper about it, and what is really interesting to see is that they use the entire amateur band from 430 to 440 megahertz for their commercial LEOP operation of their satellites, in particular outside of the United States. So that is a very interesting thing. The FCC granted a license for AST to operate these satellites in our bands, but only outside of US. So that is rather strange. So there are a couple of ground stations in Argentina, Australia, Bulgaria, St. Helena, and South Korea. The satellites are operating so they transmit and receive on the same frequency with a 50 kilohertz bandwidth, as I say, practically in the whole 430 to 440 megahertz amateur band. Very interesting here is to note that even the FCC confessed that there is no relevant service classification for those satellites to operate in this band, because this band is mainly for amateur satellites for other purposes like radio location, Earth exploration, and things like that. It is not primarily for commercial use and not for the things AST is doing. So the problem here is there was already a first example, which was Blue Walker 3, which was received by many radio amateurs. But even that one was a kind of strange that they used those frequencies. So what happened? AST submitted an interference analysis to the FCC in which they demonstrate that there will be no harmful interference to other operations in conformance with the ITU regulation. So although the satellite is not supposed to be there, they demonstrated that there is no harmful interference because nobody complained about it. So that is what I would like to put your attention in. If you see things like that, if we don't react, and you know there will be a lot of constellations going up and they are very frequency hungry, we might lose our bands. So please be careful, talk to your amateur radio organization, because it's not only the satellite band affected, it's the whole amateur radio band affected. So please talk to your organizations and take care that this is not going to be the predecessor of more to come. Anyway, in my presentation today, I would like to focus on a few things. So as you have seen, Oscar 10 was launched 41 years ago. It failed after 3.5 years because the memory died, so the computer is not working. The interesting thing is, at that time, 40 years ago, space debris mitigation and things like that were not so much in the focus. Even nowadays, every satellite needs to have a mechanism so that when the satellite fails, it will on no way continue to emit RF signals. Oscar 10 was actually operating still a few times, but then eased because more of the electronic failed, probably battery or something like that. And for the last 20 years, I think nobody tried to see if it could be reactivated. But for a little while, it was still transmitting a carrier, which was quite interesting. Oscar 40 is also still in orbit. It was launched 24 years ago, but it failed 4 years after the launch due to a short circuit in the main battery. And by design, there is no way that Oscar 40 will start to transmit from alone. It's a more complicated process. So while there is a chance that Oscar 10, like Oscar 7, might still transmit, Oscar 40 will never start to transmit from alone. So in some way, you need to send some commands to the IHU. Why I'm talking about this? Because, already a couple of years ago, there have been interests expressed by people, could we not try again, like with some of the other satellites, to start a kind of reboot project. So a couple of days ago, I digged out all my old IHU simulator, and even though I didn't use it for the last 20 years, it's still working. And at the moment, we are getting all the things back together, even the old command station stuff, the old software. Some of it is only running on RISC PCs, so even the old Windows software, it's not really running on Windows 11 or Windows 10 anymore, but we have our IPS set up, so we are going to try again. And well, some of the old team is in some way was burnt out, but we have new people active, in particular with the Aminas project, who saw all the remains in our store and said, wow, what really cool things you have done almost 30 years ago, and they want to dig into it. They want to understand and learn, and maybe in one way this could be also reused in future projects, because there's a lot of technology, mostly indeed the architecture behind, which could be very interesting still to look at it. Yeah, and if we talk another satellite, that is Oscar 100 on SHale-2, the first geostationary amateur radio transponder. Unbelievable, it's already 6 years in orbit. It's even strange to me how quick the time is running. Yeah, I guess if we get older, time is running quicker, but it's already 6 years in orbit. It still works perfectly. There is no sign of degradation, and so we are very hopeful that the projected time scale of 15 years will be fulfilled. Remember, in 2018 launched with Falcon 9 from Florida. There are not many pictures existing from the satellite itself. So the picture right, that is the so-called Melco DS2000 platform used for the satellite. That is a picture which are found in the cantina of Esheilsat in Qatar. It's the only real picture existing. The other one was here when it was launched and the separation. And indeed, actually only one picture during the early times when SHL2 was built. Yeah, since 2020, we are having Antarctica via Q100. So several expeditions started to use it. The first one indeed was in 2020 with Roman HB9HCF. He was the first operator of DP0GVN during the overwintering. And indeed, the antenna is specially made under radome to survive the harsh temperatures and the extreme winds. In fact, a couple of years later, we had to replace the antenna because during a really severe storm, the antenna was blown away. But it's very popular. Here's one example with a group of students, school kids in a school. Matthias, DD1 US, organized this school contact with Antarctica, which is still very popular. Unfortunately, there is a technical problem at the moment. We are sending a replacement unit down to Antarctica because they can't receive any signals from the spacecraft. Most likely the LNB for receive is damaged, broken. They had a replacement unit down there. We shipped one, but unfortunately they couldn't find it, so we have to ship another one. Also in 2022, we started to use Polarstern, the German research vessel, the icebreaker, which is going around not only to Antarctica, but also in Arctica and even across. So there have been a lot of very cool contacts from the ship over Q100. And here on the left, that was the first activation by Felix and Teresa, who tried if it will work at all. They had manually steered that dish. And the good results we found, we built another antenna where we got this radome and the parts of the antenna sponsored, because this antenna is automatically tracking Q100. Because sometimes the weather could be very severe, so manual steering is not possible. And this is what I like so much. And in fact, I would like to be there as well. Portable operation via Q100 is really popular. Here are two examples from Hugo and Paolo, who operated Q100 from really very nice remote locations, and it's really fun. And at that times when they are active, the band is full. Sometimes the transponder is a little bit empty. There could be some more activity, but this definitely helps. So what else? Since 2003, we heavily use the Bochum Observatory. We are very fortunate to have this 20-meter radio antenna available to AMSAT. In fact, the dish was already inaugurated in 1965. It was used for some of the Apollo missions. Apollo 11, it was used as a backup station. There are recordings of the real communication from the moon to Earth. Then in the years to come, the antenna had some problems and needed some refurbishment. And in fact, the only reason why the antenna is still there, because AMSAT DL practically got into this refurbished, upgraded hardware and software. And in 2003, Mars Express was the first spacecraft we received with further distance. So these in the past, indeed, in 1965, there were no Mars missions, and after it, so that was the first time that we really received such a deep space interplanetary mission. From there on, we have done a lot of very exciting stuff, like receiving Voyager 1. So that was a new record, and it was the first non-government receiving of Voyager 1 from a kind of private organization as we are, as AMSAT. And in fact, we sent a QSL card, which is seen here, to Pasadena, to the Voyager flight team. And I have a later picture, you will see it's still on the wall there. Also, Venus echoes in 2009 were quite interesting, where with really high power, the signal was sent on 2.4 gigahertz to Venus, and 5 minutes later we received the echo from Venus, and that was indeed the first one in the farthest ever amateur radio contact world record. So we had a special license because we were using 5 kilowatts of power with the high gain 20-meter antenna. Speaking about all those missions, yeah, sometimes I have been asked how many missions did we actually receive. I have a rough number, but sometimes I have, like in your photo book, when you are traveling and you want to see, oh, where have I have been in all those years and places. I keep more or less a log on nowadays on Twitter, where we put photos of the missions and signals we have received. So basically there's everything indeed. Most recently ESA, JUICE, Hera. We were also taking part in this IPSAT project, where these images were transmitted from the first Ariane 6. They were transmitted on S-band, and we received them with a 20-meter antenna in Bochum, completely remotely. That means me sitting at home, controlling the 220 tons heavy antenna in Bochum completely by remote. Also interesting was here that is a main control room in the ESOC control center in Darmstadt, and they had actually our web stream also on one of their screens here. So practically, it's the other way around. Is there any interplanetary probe we didn't receive? So I'm going through those pages here just a little bit more quickly. So we have received Chandra 6 around the moon. We have followed several moon missions like the intuitive machines IM-1. A lot of interesting stuff. And yeah, here's a picture I've said to you from the Voyager team. So here our QSL card is still on the wall. And indeed, Voyager is an absolutely amazing spacecraft and a fantastic team. If you imagine how long and how far Voyager 1 is traveling over those years. So we did receive signals like from intuitive machines, which was falling over. And in fact, we were the first to demonstrate or show it hasn't stopped yet. It's still there. So it was a very weak signal. We were really, really looking with our dish and with our receive systems at the absolute limits of the receive sensitivity. And we could show IM-1 is still alive, very weak, but it's still alive. And practically our observations helped Gunhilly to optimize their antenna to finally regain contact with the spacecraft, and it operated for a couple of days. And so we got direct. So why that's actually also part of our outreach. Not only because all that is a lot of fun, but also to see that we get some support. And in fact, Intuitive Machines was really happy for the support we have given here. And you always learn a lot of things by this. The same thing we did for Hakuto-R, which landed on the moon, or which was supposed to land on the moon in last April. We have been following the signal, among others, and some people really looked into the carrier and fine grain of this kind of signals, so you could see the wobbling from the spin, but even very other interesting details could be seen. For example, like here with the SLIM, we could see reflections of the transmitted signal from the lunar surface, and all this information. People like Danny EA4GPZ, he looked really into the fine details, and there was a lot of things to learn. He has some very nice articles on his webpage if you want to understand more. So, like the SLIM Moonlander and other things, there is always a lot to learn about how signals propagate on the moon surface, Doppler shift, how can you calculate antenna appointment, and so on. And we were very glad also to have the Japanese amateur radio club at JAXA representative in Bochum 2 weeks ago. It was a symposium. So they were very happy about how we supported the project and what kind of signals we received and what we could learn from it. And indeed, all that helps for future missions. Like here on the left side, we also received this little hopper, the left one. But there have been other missions like Peregrine from Astrobotic, which we received and where we had some very interesting and helpful information. There are more projects like ESA Cluster, UNO, Korean Pathfinder, very exciting stuff. And yeah, also I would like to mention here, in the past we had used different software. I think since last year we were mostly using the famous SATAM software from Alan, to mainly for our web stream, but also to decode some of the telemetry or record carriers for further analysis. Just for you to understand, we are not hacking or doing something illegal. Everything we do here is completely legal and actually part of our educational outreach mission as part of E0, the German E0 project, to really get people interested into this kind of things. So, in short words, we have received more or less over 40 interplanetary spacecraft has been tracked by us in Bochum, and mainly we are doing these things from remote, like me here sitting at home, controlling the big antenna and frequencies. Also, I do this almost daily with James Miller, G3RUH, who is very much taking care about the precise tracking, updating the tracking software and all the ephemeries we are needed if you want to track such a wide, far away object. And why is this so important? Well, look at the numbers here at X-band at 10 gigahertz. Our 3 dB beam width is only 0.1 degrees. And even on S-band, it is 0.4 degrees. So if you don't have precise tracking, you hear nothing. So that is very important to understand. So why we are doing these things, indeed, we wanted to do a couple of years ago our mission to the moon. That is still something, indeed, we hope one day to get to the moon, maybe as part of one of the landers mentioned before. We have some contacts with them. There is actually one lander this year who is very much appreciating what we are doing. And we have an NDA, so we will try to support them as much as possible. But the NDA does not exclude us to show the spectrum and other things in on YouTube in real time. So that is very kind and very nice. And maybe one day we will have a chance to fly an amateur radio hosted payload on one of the landers in return. So as I say, ham radio on Moon, Mars, and beyond, we have to think about it. How fast we will get there, we might see today, later on. But nevertheless, something we should always have a look, and there might be opportunities to bring amateur radio payload there. So from the biggest to the smallest, so the last real big spacecraft AMSAT-DL together with international AMSAT, with AMSAT-NA and AMSAT-UK and others, was indeed Oscar 40, which was a 650 kilogram heavy spacecraft into HEO. We are now going to the smallest AMSAT-DL ever did, which is a pocket cube, and which is the Amnias-1 mission we will fly into LEO pretty soon. And yeah, if you compare the weight, 640 kilogram to 248 gram, it's really a big difference. So in 2022, actually, there was the micro launcher payload competition by the German agency, the DLR. And this is actually where the project was born. AMSAT EA pushed us because they were the first one to see this opportunity. Sometimes you are in the same country and you don't know what's going on. So they were actually the ones saying, hey, there is this competition. Shall we not try to apply for it? And that's what we did. So together with LibreSpace, AMSAT Spain, also with support from ESERO Deutschland, we made the proposal, which we called Erminas, to be launched on one of those micro launchers. So what is Erminas? Erminas is a syndicated multi-pocket cube mission. We have our own pocket cube deployer, which was developed by LibreSpace, and it contains theoretically it can contain 8 pocket cubes. In our case, we have 7 pocket cubes. Why? Because 2 of the pocket cubes are 1.5 P standard. So the standard 1 PQ format is 50 by 50 by 50 millimeter with a mass of 250 gram. And these 2 are 1.5 PQ size. So that's why we ended up with 7 pocket cubes. So we will have 2 pocket cubes from AMSAT-DL. That will be Erminas-1 and U and 1V. 1U operates in the 70 centimeter band and 1V will operate in the 2-meter band. Then we have the satellites from Spain, UNNE-1 and Maria G. They transmit on 70 centimeter, but they also have a transponder with 2-meter uplink and other nice experiments. Then there will be the Cubic 5 from LibreSpace, and also because LibreSpace delivered the deployer, we gave them the opportunity also to have 2 of their ZITLOC PQ1 and PQ2 satellites, which will be used for spacecraft identification and localization project, which is funded by ESA, and they are indeed not using amateur frequencies for that. So that is the basic design of a pocket cube, which is actually a standard design based on the cubic design from LibreSpace. So we had a very short time frame, so we had to look, okay, what can we do in this short time? Because we have a P3E sitting around, but it's too heavy and too big. So we were looking, okay, what can we do? And fortunately, the original design from LibreSpace is open source completely. That means open hardware and open software. we had to do some improvements. There were also a few things which were probably not in the documentation and had to be changed. We found that out, but mainly we're following here the cubic open source standard from LibreSpace. The only differences I marked here is that indeed, typically they always use the 70 centimeter band. We will use the 2-meter band for the first time. So having a larger antenna, we will use micro SD card, which stores images. So we will transmit SSDV images and other information which is stored from the micro SD card. Unfortunately, there is not enough power and not enough room to really have a linear transponder, which we would really like to have, but it's the beginning. That is a basically short block diagram. So we have on 5 sides, we have solar panels, then we have charge management, power regulation system, a battery, and then some of the payloads. So here in red, I marked where we made some changes. We made some same changes on the receive and transmit part to adapt it to the 145 megahertz band because it was originally designed for 435. We have added a sensor board and we made some changes on the antenna. This is the AMINAS-1 sensor board. It will fly on both AMINAS-1U and AMINAS-1V. You have seen that probably yesterday already. We will also use a radiation sensor, this famous BG51, which you see here. It's the OEM version with no plastic cover and so on. In addition, we have a 9-axis IMU, which is practically triaxial accelerometer, a triaxial gyroscope, and magnetometer, 3-axis magnetometer, all in one case, which is this part here. Then we have additionally Bosch BME 280. We mainly use it as a very good temperature sensor, but actually it is also able to measure humidity and barometric pressure, which doesn't make sense in space indeed. But this board can also be used, for example, on balloons and other things. All the hardware, software developed by our team is also open source, and we have a GitHub repository where all this is stored. We made some optimizations on the antenna. So instead of this stretched dipole, we will use an angled V dipole because it gives a very much better antenna pattern. A straight stretched dipole has these very deep dips, and the problem here, it could be very problematic. If the rotation of the satellite is in some way synchronized with these deep dips here, it can happen that due to the ratio of frame length and rotation speed, it could be possible that we cannot communicate properly. So to improve this, we have made changes on the antenna, and indeed, we hope that this will give better signals too, something we still to be seen. Now, let me see if that works. For some reason not, so that is, I don't know why. It should actually run, but it doesn't. That's too bad, because I wanted to demonstrate how the antennas will undeploy, which is quite spectacular. But I don't know why this is not possible to play on this screen. It runs in my original presentation, but not on this screen. Sorry for that. Well, here's the AMINAS team. So we have a couple of people. Also, that was during one of our meetings in Bochum. We had Fabian Manoles from LibreSpace visiting us, and then indeed Tillman, Nicole, myself, Patrick and Tillman are the key persons here, and Thilo So myself, I'm being the overall mission manager and also the contact person with all the agencies regarding the overall missions, also with our partners from LibreSpace and AMSAT Spain. So Tilma and Patrick, they are actually the project managers in terms of hardware and software. We had Jens, he was building the first prototypes. Holger, DF2 FQ, our RF and antenna expert, who actually looked into the design of the antenna, and a few more people working on this. So mission goals, indeed, can we do such a project with minimum budget and resources available? Remember, for this project, we had no external funding except for the ride with Rocket Factory, with a free ride, but all other costs involved, even getting the things to Saxaford, still costs money, which is basically coming from our membership. Indeed, another goal was creating a new team. Most of the people have never touched a real satellite before. Probably I'm the only one left over. I'm getting old. So also important to get all the know-how transferred and learning by doing. And sometimes it's easier to tell people what is right or not if you're doing it. So that's also kind of know-how transfer. Also, we are trying to get cooperations with partners, Sternwarte, Bochum, others. Indeed, we want to contribute to amateur radio, satellite community, with a satellite for everyone, basically. We want some kind to produce satellite kits for radio amateurs in schools to experiment with it. And indeed, we want to scale up for missions to come. We have built a small clean room under the Radom in the Sternwarte, where we have the right environmental actually to work on such projects. So here on top of this box, you see the airflow, laminar airflow and filtering, so that we really have good working conditions there. Indeed, there is a lot to be done. Vibration tests, shock tests, bake out. So test is very important if you want to have your spacecraft surviving. These were early tests with engineering models. After building the flight models, we did shake tests at the Universidad Politécnica de Madrid. We are very thankful for our partners from Hyra Space and AMSAT Spain, mainly here Pablo, Felix, Marina, which were very helpful to organize that we could really do these shake tests with our flight hardware and the deployer. And indeed, here we have Thanos, Andreas, and Elias from LibreSpace. And yeah, spacecraft was traveling a lot by train, by car, airplane, and now we are looking forward to launch with a rocket. So we have done all the final integration in August, a couple of weeks ago. We basically put everything together, flight ready, lots of happy faces, but then what happened? As I told you, we are going to launch with Rocket Factory 1 on their rocket, and here on the right you see the UK spaceport in Saxaford. That is where we are going to launch. In a couple of weeks ago, actually that was one day before we did our integration, there was supposed to be the hot fire static test of the first stage. Unfortunately, that stage, well, was blown away. There was spectacular fireworks, not what we expected. There was an anomaly which practically destroyed the first rocket stage, which was supposed to launch us later into space. So that was a kind of shock, but on the other hand, these kind of things happen, and better now than later. I can tell that Rocket Factory was very transparent here. Already the next day, they called me and we had a discussion where they explained what happened. They felt very sorry about it, but my reaction was actually no, not to be sorry. That is something, if you have a new rocket, these kind of things happen. We experienced that in the past. Even SpaceX Falcon 1 was only successfully on the fourth launch. So as earlier we find these kind of problems, there is a better chance that we will hopefully get a successful launch. I see I'm having, I only need 5 minutes, so don't worry. So the lessons we learned, no matter how big or small your satellite is, the administrational work is the same, even like building a big one. I'm saying this because it's not only about building a satellite. You have a lot of contacts. Indeed, you have the launch contract and all the related documents. You have to make space debris analysis. That is what we do with DLR. Then you have to do with Bundesnetzagentur. That is something like the Ofcom in UK, the governmental organization which takes care about frequency assignments, ITU, IAU, so that you get all that stuff. And also we have to, because we are launching from a British soil, we have to work with the UK Civil Aviation Authority, the CAA, and there is a huge amount of documentation. Practically, this is a job for one person, a full-time job, and I had to do that in my free time after work. So because I have a real job, never forget that. So there are a lot of things, and that is something also David and my friends from AMSAT-UK will run through it. The first step is to get this green or yellow in this ample light, but then the real work begins because you have to provide a huge amount of papers regarding national security, national interest, international obligations, fit and proper persons. That means, am I personally a proper person to do these kinds of projects? Or do I have bad records with police, or I don't know? Is our organization fit? Financial assessment, is our organization in fitness, and so on. Insurance. There is a lot of things. Technical assessment. They look into every detail. How do we ensure that the spacecraft, if it's not used or damaged, that it stops transmitting? Cyber assessment. Is your ground station secure? Can nobody hack your ground station? Ofcom review, export control, and so on and so on. And you see that takes a while. So we already started last year, but in May we got into the details, and finally in November we still waiting for it, but we wait for the grant license to actually launch from Saxeford. So yes, we can, size matters, and we want more. So maybe another Erminas mission proposal is underway. We are building up our ground station in Bochum by adding more antennas, especially for LEO satellites. We had another mission in proposal. Time is too short to go to this. We planned for Artemis 2. We hope for Artemis 3, a CubeSat demonstrator for deep space communication, also by using the Bochum 20-meter antenna, indeed, if we go behind the moon. We are working with University of Bochum on some CubeSats, some of those flat. You might remember this kind of design from the Swarm satellites I tested a while ago. Unfortunately, their service ends in December 24, but there are still a few things to be learned, and they have a very interesting concept of their quarter U design. So we want to upscale that so that we can fly first on the quarter 1U, that we could reflow some of our pocket cube PCBs, and even to a 1/4 4U, where we can actually have more in it. Okay, so I'm at the end. I can control a satellite from home. That's true. That's a while ago. But now we we look forward what brings the future. So that ends my presentation. Thank you very much. And yeah, if you have questions, I'm happy to answer them.
Well, thank you very much, Peter, and it's been absolutely fascinating. And I've got a bunch of folk here, all absolutely gagging to have a go on your 20-meter dish, or maybe they can try and see if they can figure out they can build a 20-meter dish in their own back gardens. So anyway, yes, thank you so much. We have a little time for some questions. Anybody? Yay, there's a few hands gone up. So here we come, Peter.
Hello, thank you for presentation. Given the size of these pocket cubes and open source design, how feasible it would be for individuals to actually build a tabletop model with a real thing, maybe with less expensive components?
I don't understand. I'm not sure if I got your question right. So your question was if individuals could build something like this or
yes.
rebuild their own pocket cube.
Yes, if they could build their own hardware and then submit it to you for launch. No? Oh, just on the tabletop, just to play for it. Yeah, okay.
Yeah. Okay. So in principle, yes, but unfortunately, there is indeed not so much room on such a pocket cube. So I try to figure out how to get back to that picture. This overview. So yeah, there was one board left here, the sensor board. That is the one we added. So in the original Cubics design, they have some masses there to increase the mass of the pocket cube. So if your pocket cube is more heavier, you have a longer lifetime. If it's lighter, so they had some masses added. We removed that and put our sensor board in. Indeed, instead of a sensor board, it could be possible to have some other kinds of interesting boards there, maybe camera processor or some other thought. So definitely this is a standard design. So all the boards have this kind of interconnector. They use I2C. So definitely it's possible to actually, instead of the sensor board, to have your own board here. That is definitely possible.
Thank you, Peter. This is Graham, VZV. Great presentation as always, so thank you very much for that. I've got two questions. You may decline to answer one or either of them or both of them. First question is, are you able to tell us at all about what actually happened during the test at Saxaford? And the second question is, you've got experience now of dealing with UK regulatory authorities. You've obviously got previous experience of dealing with other national regulatory authorities. How would you say the UK experience, how does it compare? Thank you.
Mm-hmm. So first of all, yeah, this hot fire static test, which, well, ended in the fireworks. Actually, all what I have here on that page is not NDA. So already in the next days, Rocket Factory Augsburg gave some first hints what might have happened. They even had a further analysis published later on. Indeed, at the moment, they are still analyzing. So what so far is known that there was a problem. Actually, the problem was not in the engines or something like that. There is probably it's not a design problem what they found out, but maybe some materials were not within the expected spec. So something was broken there. I think they have learned already a lot. They are still doing fault analysis, qualifications. They already have a new stage. Actually, we will fly what was supposed to be the second flight. So the first stage from the second flight will be used now for our flight. They have already done a lot of improvements regarding the launch, yeah, somewhere in summer next year is what we expect. But as I said, they have to concentrate now on the qualification, on the analysis. So there's not much to say about in detail. That we have to wait from them. But as I said, they have been very open on that. That was actually nice to see and very different to what we usually see with the traditional big companies. So regarding your questions with CAA, what should I say? If I would have known before how much work I will be confronted with and how many questions, I don't know if I would do it again. On the other hand, okay, now since I have done it, I got a lot of knowledge, what kind of questions, and sometimes it's really like boring, and you ask yourself, why in the hell do they want to know this? What is their interest? But at the end, it's easier to scope with it and just give them the information they are looking for. Honestly, and we have a very good, really excellent relation. We have every Monday we have our teleconference, and it's very nice people, and it's really good talks that I have to say. And for them, it's also a learning lesson. And they already told us we were the first. We are the first they worked with. And actually, we were the first. We were really speeding up. We were the first to get in touch with them and work on these issues. And they understand, okay, they might have to change some of the processes. So at the end, I can only say positive things. It is a lesson learned. It's a lot of work, but working with the people is fun, and even we learn a lot about it. And I hope that some of the things we got will help you also to go through all those details they ask for. So, yeah, it has to be done, and everyone is more careful also in terms of space debris mitigation and how to ensure that the spacecraft will not be a problem for others. In fact, that is a problem for a spacecraft as small as a pocket cube because they have problems to track those little objects, and they are more concerned launching them into higher orbit than into lower orbit. So, because let's say in 400, 500 kilometers, they can collide with other objects, and yeah, they say, okay, why should someone else try to avoid to collide with you? So you also have the obligation to do everything. So in orbit propulsion, orbit change, these are the things which will become more and more important in future.
Very good. Thank you very much, Peter. That's a very concise and comprehensive answer.
Yeah.
So, any more questions for Peter? Nope. Okay, well, thank you so much, Peter, for your contribution. It's been a really marvellous presentation. We're now going to break for lunch, and thank you so much for joining us. And a round of applause for Peter, please.
Yeah, thank you very much. And yeah, I enjoy your lunch, and later on enjoy the spaceship launch.
Yes, we're very much looking forward to that. We hope it'll happen. Okay.
I will
Three
too.
for now, Peter.
Thank you. See you next time.
Right, everybody. We are. Can you hear me? Working out? Yeah. It's been very much an international day today with Peter this morning and the Starship and so on. Now, pleased to welcome Ernst Fish about AMSAT-NA and what's going on in the States, which should be very interesting and a most important session of this. Burns.
Okay, thanks. Hi, can everyone hear me okay now? Just okay, very good. I wanted to check. And I should be able to share, I guess. Let's just see how this works. Share. Hopefully you can see that now. And
yes, we can. I enabled sharing earlier.
there we go. Okay. Someday, Zoom and Microsoft are going to get together so that one can expand the PowerPoint slide at the same time that you can see everything on Zoom. So anyway, I also want to. There we go. Can't do this ahead of time because you just don't know what's going to show. Anyway, welcome. Thanks everybody for listening. I'm Burns Fisher. My call is Whiskey Bravo 1 Foxtrot Juliet. I'm a life member of AMSAT North America, and I volunteer for AMSAT as the lead flight software developer for our Gulf satellites. This software is also the basis of the software that's in LTM radio sets that we provide to university partners, our upcoming Fox satellites, Fox Plus satellites, I should say, and the PACSAT payload. And all these I'll be talking a little bit about later. I want to talk in general about a few things. So the kind of general subject is stuff that AMSAT-NA is doing, but I want to talk about the Gulf project. You've probably heard about the Gulf project for many years. It's been, shall we say, long running, but things are moving along more now. The Fox Plus program, a kind of revitalized program called Ascent, which I will translate that acronym for you as soon as I remember it myself. The LTM program, which had a launch in July, and I'll also point out a few current satellites that are available for use. And speaking of a launch in July, boy, that was exciting to see today. I didn't tune in time to see the launch and the catch of the first stage of SpaceX, but I saw the landing of the Starship, or quote land. I guess it's more like the oceaning of the Starship, and that was pretty cool. So I'm glad you all got a chance to see it as well. Let me just bring up before I start, I wanted to mention a few anniversaries that are close to today. AMSAT UK's FunCube 1 11th anniversary in orbit is coming up next month, I believe. You might recognize this picture that I put on here as the NEPA rocket launching FunCube. So that was pretty cool. Special to me, since it's the first satellite I worked on, is AMSAT-NA's Fox 1A, and its 9th anniversary was last week. For both of us, exciting moments to hear each of these satellites for the first time. And of course, we have the grand old man of satellites, AO7, 50 years and still operating when it's in the sun. Now, I can mention these anniversaries, but of course, if you do the probability calculations, given that there are 122 Oscars, the probability of some anniversary for one of them coming today is about 28%. So maybe it's not as exciting as I thought it was. So let's go on with the Golf T program. Golf stands for Greater Orbit, Larger Footprint. Everybody wants a higher orbit. We would love to have more higher orbits. The Green Cube managed to get one, and that was a wonderful thing. We had somebody here in the eastern United States that was able to get their work to all states by satellite certificate by reaching Hawaii, which is way off several thousand miles to the west of the western United States by way of Green Cube. So that's a nice thing. But we'd love to have more satellites in higher orbits. Unfortunately, the regulatory environment in the United States makes higher orbits very difficult for small, non-commercial organizations like us. But we have one group of volunteers that's trying to work on that, figure out what we need to do in order to get to a higher orbit regulatory-wise. But in the meantime, Golf T is moving ahead to launch into low Earth orbit. Its plan is to develop technologies that we do need, that we'll need in the satellite itself for higher orbits. Our current thought and hope is to launch in 2026, but we are not manifested on a flight yet. So again, Golf T's goal is to gain experience with and develop technologies to test in low orbit that will be needed for high orbit. So let me talk about the Golf T satellite and a few of those technologies. First off, there's a 10 gigahertz downlink test and several microwave uplinks. And why do you need microwave for high orbit? It's because in the higher orbits, you need some sort of a directed antenna. And a directed antenna is going to be huge for the usual 2 meter, 70 centimeter sort of thing. So we want to have a microwave downlink that we can use much smaller antennas on. Golf T will be fully attitude stabilized, and the reason we want to do that is to allow deployable solar panels and get more power. The panels will deploy, and they're all pointed in one direction. So you want the satellite pointed towards the sun. And similarly, the microwave antenna wants to be directed towards the Earth. Now, you can't always do both at the same time, but at least we can move back and forth between Earth pointing and sun pointing. We also have a redundant IHU onboard computer, redundant command receivers, redundant telemetry transmitters, and so on. But we will also have a traditional 30 kilohertz VU linear transponder. So I mentioned that we've been talking about this for years. There have been a huge number of delays. A key member of our team and a good friend became a silent key. Bob Davis, if you ever know KF4 KSS, died in the middle of bringing this whole thing up and in the middle of the pandemic. So, it's just a horrible problem and a horrible situation for all of us. The supply chain problem that the pandemic caused for us, the ADCS and power system supplier that we were planning to use couldn't deliver. I don't know if they're actually still operating or not. They just had such a problem with the pandemic. And of course, delays also mean parts that are going end of life. So we need new designs. We need new volunteers. And with the new volunteers, we need a new training regimen. So all of this stuff has delayed golf enormously. But we do have the program going ahead now with many new volunteers. So let me show you what Golf T is supposed to look like. This is a diagram, and it's from over a year ago. So things have changed a little bit. And in addition, this isn't quite to scale. But to give you a general idea, this is sort of what it will look like. 3U, of course, means the satellite is about 10 centimeters in width and depth, about 30 centimeters long. Now, I don't have to explain this to you guys. For US audiences, I have to say 4 inches by a foot. So it's nice to be able to stick with metric. You can see there's a sort of standard longitudinal stack. I'm going to try to move my mouse, which I think you can see here. This is one of the, this is a standard stack. It's very much like our Fox stacks with a processor, an RxTX transmitter receiver, command receiver. But now we've added on some experiments, and we've added on this redundant processor system, as well as the redundant, we call it the DCT, the transmitter receiver. Down here is the EDIS. We are using an EDIS E310 to do the microwave work. And over here is the attitude control system, the ADCS, along with the power system and a few other odds and ends like the microwave, the power amplifier. So I just will show you a little bit more because we've been doing a lot of work. The ADCS in particular has upgraded from Gen 1 to Gen 2, and I'll be talking a little bit more about that. But we've also been able to generate appropriate models of this. So our mechanical designer recently got all kinds of STL files of the design, and he got them pieced correctly so he can build a 3D printed model of the satellite. So you can see this is very similar, except it's an actual photograph. And you can also see that the ADCS looks quite a lot different down here. And there are a number of different boards here that have changed a little bit in the last year. But this is much closer to what we're working on now, although there is some tweaking continuing. Come on, there we go. So this is what Gulf T actually looks like right now. This is my shack. And we call this a flat sat for obvious reasons. You probably do the same thing on your satellites. Out of sight to the right. Whoops. There we go. Out of sight to the right is the EDIS 310 transmitter and receiver. That'll be used to receive the microwave uplink and will be connected to a 10 gigahertz upshifter and power amplifier for the 10 gigahertz downlink. There we go. In the right, and you can see it there in circled in red, is a stack consisting of the command receiver, a 30 gigahertz linear transponder, UHF telemetry transmitter, as well as the 2 onboard computers. 2 of those boards are legacy fallbacks in case the new stuff doesn't work. 1 onboard processor and 1 command receiver. We, for future Golf Ts, may not need to use that. We will use the RxTX most likely because that contains the linear transponder. Now the red circle has moved. In the center with that gray cable connecting it is what we call the central interface unit. It's the central connection point for lots of satellite pieces, including the longitudinal stack, which you could see on the right. That's where the EDIS will connect in. That's where the antennas will, or the antenna release mechanisms will all connect in there, as well as the GPS, the power supply, and so on. So it's not terribly exciting in many ways, but it's really important. You can see a USB connector down there at the bottom. So that USB will be the umbilical connection for when the satellite is all put together into a 3U package. And that will be how we will access processors and everything else when it's packaged, but before it's placed into the launcher. On the front, on the left there, is the GNSS unit or a GPS circled in red. Behind that is the development model of the ADCS, and that should be circled in green. Yes, I can see it. There we go. Over here, the development model is just kind of a square box here, with this connection plugged into it with the cables going to it. And the things that are circled in blue, which are here and here, are development kits from the manufacturers of the ADCS and of the GNSS systems. They're pretty huge. They make it convenient for us to do testing at the moment. They're not going to fly. The GNSS system here is the only thing that's going to fly. That's pretty tiny. And the ADCS here will actually fit on the longitudinal stack as opposed to the transverse stack, which is here. Okay. So that's what the current system looks like on my bench. Of course, it doesn't give me much room for anything else. So let's look at a few of the individual pieces. This is the RTIHU, which stands for Radiation Tolerant Internal Housekeeping Unit, or we hope it's radiation tolerant. How this is made is it's got two processor chips, one here and one here. These are both automotive grade processors from TI, Texas Instruments. So they have a lot of redundant stuff in them. They have an EDAC, or error detecting and correcting memory system, parity buses, and actually within each one of these processors, there are redundant cores, and the cores are actually in lockstep with each other. And if something goes wrong, and they don't, they're continuously being compared. And if they don't compare correctly, an error flag gets raised. And on our board, the error flag causes us to switch from one processor chip to the other processor chip. So there's a lot of redundancy built into this thing. The two redundant board halves have two processor chips. I can point to the processor chips. I'm not sure I can actually figure out which of these devices is which. Besides the processor chips, it has a non-volatile memory chip called an MRAM. It has a command receiver and telemetry transmitter, and either one of these can double as the other. In other words, if one entire side fails, then that one chip, the command receiver transmitter, can do both. It has to switch back and forth between receiving and transmitting. But if there is a massive failure, we still have transmit and receive capability. What I can point to is in the middle here, these are bus switches. So the failed side of the RTIHU is kept off the satellite bus, or it doesn't even have to be failed. Only one of these sides is operating very much at one time, And that's the one that's connected to the satellite bus. So that's the RTIHU. The ADCS, the Attitude Determination and Control System, this picture is the Gen 1 version of what we plan to use as the ADCS system. We'll be using the Gen 2. You kind of saw the Gen 2 in that picture on my bench. It's not very interesting because it's the Gen 2 comes all enclosed. So this is more interesting. It would look fairly similar if you were able to disconnect the Gen 2, or sorry, take the outside off of the Gen 2 system. We are buying this from a company called CubeSpace in South Africa. I was in South Africa for another purpose this summer and was able to stop and talk with them and ask them some questions. So that was quite a fun thing to do. We hope this will work nicely. We're probably not going to use the star tracker that you can see on this picture. We're only going to have a sun and an earth tracker because we don't need that fine control. We currently just have a development model. The development model doesn't actually have all of the devices, the actuators and the sensors, but it does have the capability of talking to, over the communication buses, so that I can develop the software to communicate with it. We also have software that will simulate being in orbit and will simulate more of these devices. So we should be able to do a lot with the development system, even before we have the flight and engineering models of the full ADCS system. This is the CubeSpace Cube computer, the board that we got initially. But we do now have the Gen 2 version, which, as I said, is all enclosed and a lot less interesting to look at. We have it, I just last week got it connected to the satellite onboard computer, and I've been talking to it over a CAN bus. I2C will be coming as a backup, and we can also talk to it through a UART, that is a serial line interface, and I'm leaving that to be able to connect with a PC and their CubeSpace's testing software. I may have mentioned, I think I did mention that we were going to get a power system commercially, but that purchase fell through because of the pandemic. We got some new volunteers recently who were interested in designing and building it. So we said, sure, let's, the more we can design and build ourselves, the better off we are. We want to do that. So this is an early prototype of the MPPT. MPPT stands for Maximum Power Point Tracker. If you're not familiar with the way solar cells work, they give a different amount of maximum power depending not only on their temperature and the sun angle. I mean, it's not surprising that if the sun isn't directly at them, they're going to give less power. But the interesting thing that you need to do is to tweak the voltage and the current that you're pulling from them in order to maximize the power that they will give. And that's what the MPPT does. We also will, the same group of people is designing a battery management system to maximize the battery life and safety, and a power distribution system to provide the actual correct voltages within the satellite. So you can see there's a evaluation board for one of the processors right here, as well as the other stuff that they're going to test. This is, I believe, where some batteries are, some batteries are going to go. Sorry. So the current state for the Golf T is that we are going through preliminary design reviews. We actually did do the preliminary design review for the power system last Wednesday, and that came out pretty well. We had some questions, and the designers are going to answer the questions, and hopefully we had some good ideas that they can incorporate into their final design before their critical design review, which will be coming up probably mid next year or early next year. So you can see that we have a lot of prototype boards and a few boards that we would even say are engineering model level boards that are under test. And most of those boards are under test in the flat sat that you saw the picture of earlier. The space frame design is making good progress. Again, you can see that it's good enough that we could make 3D printed models of it. The next thing that the mechanical engineer fellow is going to do is to actually bend some metal and make metal models of it to make sure that all works. The deployable solar panels are also making good progress, and the metal tests, the metal bent metal, space frame design will allow us also to test out the solar panels. They've got to be able to fold up on that space frame and to unfold without breaking themselves. So that testing will be done. So being the software guy, I will tell you a lot of software has been done for years. Unfortunately, a lot of the software also requires talking to and commanding and sending down telemetry from new hardware that we're only just starting to get. So there is still a lot of software work to do, but the software that knows how to deal with 3 different processors and how to choose which processor it's going to use, how to collect telemetry from all 3 processors and have only the active processor send the telemetry. All that good stuff has been done for quite a few years. But there is still a lot of work to do in the software realm. Golf T has been accepted into the NASA CSLI, CubeSat Launch Initiative, and Alana, what does Alana stand for? Something educational launch of nanosatellites into that program. It is not manifested for a launch yet, but we've passed the hurdles through NASA to say, yes, we think that you belong in this program. And to be honest, 3 of our Foxes also did the same thing. They went through Alana, and that's how we got the launches. And the good news is the paperwork weight is approaching the weight of the satellite. So that means it's going to be ready to launch pretty soon, we hope. So as I think I mentioned briefly earlier, we hope we'll be ready to launch in 2026. We do have a lot of potential worries. And once we are manifested, the actual launch date is pretty much out of our control. Some of our satellites have waited a few weeks after the original specified date. Some have waited a few years after the original specified date. It all depends on the launch provider. NASA tends to use new launch providers to launch CSLI satellites, and new launch providers tend to have a lot of delays. So we'll talk a little bit about that in a minute for some of the other satellites. So that's the Golf T state. By the way, if anybody wants to ask any questions, do feel free. I don't know how how it works with golf, but if someone can type in into the um,
Yeah, Burns, we usually leave questions till the end of the talk, if that's okay.
okay, yeah, absolutely. That's absolutely fine. Thanks. Sure. Okay, so Fox Plus. Now we've gone through Golf T. Fox Plus is a new program. Fox One, which was AO 85, 91, 92, and 95 was in there as well, and 102. They were mostly FM satellites, which were, and especially those three, were popular, but they have mostly failed now. They had NiCad batteries, and NiCad is supposed to be okay for lots of charge and discharge cycles, but the temperature thermal environment that we predicted was not what we actually saw according to our telemetry. So I think that's probably one reason that the batteries failed sooner than expected. AO91 is still operating, although I think there isn't enough voltage to run the processor. So we're not seeing any telemetry from it. I do see that there are some people that are still using it as a repeater. But AO91, when it is running, SO50 and any of the FM satellites are really crowded. Their FM is popular, and but since only one can use it at a time, that makes it more crowded. So we need more satellites quickly and soon. FMs are easy and inexpensive to use, lightweight equipment, easy to do remote operation, but more linears also reduce crowding. And so the point of Fox Plus is an attempt to be able to launch satellites that build on Fox One with some improvements, but also to be able to launch them relatively quickly. You know, we wanted to be able to just use Fox One with some slight upgrades, but so many of the components we found that we used in Fox One are obsolete and unobtainium, as we say. So you know, they're just not the stuff to put in them isn't available. Not to mention, as I said before, our mechanical engineer from Fox One is a silent key, so we have to restart some of the mechanical work. So Fox Plus is both trying to recreate Fox One with new ideas and components, as well as using a subset of the golf boards, which are all you know, being worked on currently, as well as purchasing some pieces whole. So the Fox Plus philosophy, build on Fox One, build on work done for golf. By the way, Fox Plus One can also flow back to golf. Fox Plus can flow back to golf. We want Fox Plus to be open source and access and all documents to be on GitHub or GitLab. There are a few that are NDA docs from purchased stuff that we can't make open, but we want to as much as possible. Why do we want it open? Because more grants are available and we avoid ITAR issues. Now, ITAR is unfortunately a US regulation called the International Traffic in Arms Regulation. Some parts of satellites might be considered armaments under the ITAR. So in Fox and Golf, we have to be careful only to have US persons, that means mostly citizens, working on them. Making everything open source takes advantage of a cutout in these regulations, so we aren't covered by it. And then, as I said, in addition, some grant sources require open source development, allowing us to apply for these grants. So between those two reasons, We want it to be as open as we possibly can. Notice that we still have to pay attention to other regulations called EAR, export administration regulations, if we actually export hardware. Luckily for us, low Earth orbit is not considered an export. But if we were, for example, to launch on, well, we can't launch on Ariane anymore, but if we were to launch on PSLV or any of the ESA launchers or anything like that, that would require export. So we'll probably mostly be launching on US launchers. Later Fox Plus satellites might well have more capabilities than are here. Fox Plus A is going to be just a 1U, magnetically stabilized. That is, it'll have a bar magnet in it that will attempt to follow the Earth's magnetic field. The space frame, power, solar panels, all purchased for speed and development. Later Fox Plus versions may be bigger and pull in work from Ascent, which we'll talk about in a minute. And that includes a new packet satellite payload. Think FalconSat, if you've had any experience with that. Actually, you might not have been able to use FalconSat in the UK, because I wasn't either. It was a fairly low inclination orbit. So the Fox Plus A status, we have a number of new volunteers. A system engineer are recruited. As of now, there's a meeting concurrently with the golf team, at least among members that are vetted for ITAR, because that meeting is considered ITAR. We do that though to get cross-fertilization and to help with onboarding of new volunteers. There's hardware on order. The antenna has arrived. The solar panels are going to arrive soon in the power supply. The preliminary status review is coming up, and that's actually a pre-PDR type of thing. It's just looking at what we need to do next. Optimistically, we might launch before Golf T. You know how that works. Yeah, that's what we would like, but it's probably not going to happen. This is being the first one of a new generation. Future Fox Pluses, B, C, and D, they're likely to be larger, a 3U size of CubeSat. That will allow for deployable solar panels, giving more power. More power gives more capabilities. And we can take advantage of Ascent and other new payloads. In fact, Fox Plus B is going to carry PackSat. And I'll be talking about, I keep giving you these little hints that I'm going to talk about Ascent later. The LTM program is another AMSAT program. LTM is a set of boards that we make available to universities that want to do their own experiments. They want to do experiments, they want to do things in orbit, but they don't want to bother with all this radio stuff. They want to build something else. So we give them commanding and telemetry. When they're done, sometimes while they're operating, they agree to turn on an amateur radio linear transponder. The LTM consists of 3 boards, essentially identical to those that are going to be used in Fox Plus and as part of Golf. The RXTX is the receiver transmitter, the LIHU is the onboard computer, and the ICR is the improved command receiver. So 2 of these LTMs have flown so far. One is the University of Washington, HuskySat, that was several years ago. And the University of Maine, MESAT-1. And I have some slides on MESAT-1. We'll talk about that in more detail later. For those two, we did a lot of customization. But if we want to keep supplying LTMs, we just don't have enough volunteers to customize every board set for every university. So starting with the next ones, we're going to try to do something different. We have created a generic interface control document. And it essentially says that we give the university some specific downlink channels of data channels, some digital, some analog, a few specific I2C devices, as well as the ability to send their own data as CAN packets, which they can define. We give them some specific commanding capabilities, and we give them the ability to send their own commands. But essentially, each one of these LTMs that we will give to a university is the same. And what they want to be different, they do themselves. We give them the capability of doing themselves. So we hope that will both get more linear transponders in orbit and save us volunteer time and handholding, if you wish. Oh, huh. I had to. Anyway, yes. The LTM, again, I guess we don't need this one because it says the same thing. But one of those LTMs is called AMSAT-1. That's our current university partner. They just launched last July, and this was a very long delay. It was a long delay because it launched on the Firefly launch vehicle. And Firefly is a brand new launch partner of NASA. Firefly had done a lot of testing, and they had a few failures. They want to get into the launch business, the quick launch business for the defense industry. So they had a few special launches for the Department of Defense. So anyway, this delayed actually literally 2 years, I think, from what was originally planned for AMSAT-1. But it finally launched. The launch went well. Things seem to be going well with the satellite. AMSAT-1's science mission is multispectral imaging of Maine estuaries. This is the point Maine is the northeastmost state of the United States, and there are a number of rivers going through Maine and emptying into the ocean. And that place where where the rivers meet the ocean is what they wanted to study. It does have the LTM amateur radio 30 kilohertz transponder. The telemetry is receivable by anyone using the newest version of Oxtelem, and that includes the science downlink. So if you want to receive telemetry from AMSAT-1, we appreciate it. Any telemetry is helpful. The current status of AMSAT-1, it's in orbit, it's transmitting telemetry. The linear transponder has been running for several weeks, but just yesterday, I think they turned it off. This is all still experimental, so they want to save the battery and check how the battery recharges and all that sort of stuff. The picture taking story is mixed. We do get picture data, but there's no image visible, and that may be because AMSAT Ops has been helping because of the launch delays meant the original students have graduated. Always a problem with universities. So Maine is trying to get new students to run the experiment, but in the meantime, AMSAT has no expertise in how that all works. Maine is trying to get new students and take over the science. The ASCENT program, now here's what it stands for: Advanced Satellite Communication and Exploration of New Technology. Our VPE, Jerry, is Vice President of Engineering, is really big into making acronyms. Think of it as R&D. The idea to develop new ideas that we don't have a specific satellite use for. In fact, the original Ascent program developed some concepts like the RTIHU, the microwave RF in golf, but it was largely oriented towards developing technology for a commercial partner. Anyway, Ascent went into hibernation for a while, but it's back now. Current Ascent projects. The 3U space frame with deployable solar panels is considered Ascent. It's partially funded by ARDC, Amateur Radio Digital Communications. Interesting story about how they got a lot of money to give out, which I won't spend any time now on. They are a private foundation existing to support amateur radio and digital communications. So thank you to ARDC. They're looking for projects to fund. They are not US limited, so feel free to consider them if you need money for something. This space frame is likely to be used for both Fox Plus and satellites for golf. More golf than Ascent, but it is open source. AMSAT developed some reaction wheels. Somebody wanted to do it, so we've developed it. This is still in the very early development stage. There's no software for them yet, but that's why it's an Ascent project. We're doing a homebrew microwave receiver transmitter to replace RX in future golf and later. And we have a just graduated Ascent project. There's a packet satellite for a packet store and forward. It's got four receivers. Here, AX5043 chips are the receivers. It's got a TMS 570 processor, and it's got a single AX5043 or transmitter. So it's packet store and forward, multiple uplink frequencies, and a multiplex downlink. So think of it as a mailbox and file distribution in the sky. Now that was developed under Ascent, but we're planning to fly it on a future Fox. So we no longer call it Ascent, but I'll still talk about it here. Here's the PackSat Proto, and I know I'm coming to the end of my time, Ian, so I'll try to go fast. PackSat prototype that you see here, which was designed to go with an evaluation board, which is the red board underneath it for the processor. Then we went to a PackSat prototype board, which is a full prototype that has the processor on it and so on. Lots of software has been written, the onboard file system, packet receiver, packet transmitter software, telemetry downlink, and commanding. All this stuff is written on the old, on the Proto 2, currently working on a new board that will go on the Fox Plus. So I'm just going to very briefly talk about current AMSAT-related satellites that are in orbit. AO91 is there. You can see the frequencies. The batteries are very, very unhappy and getting worse. So we don't know how long that will last. There doesn't seem to be any telemetry coming now, but there are repeater ops. MO122, MESAT-1 was recently designated main Oscar 122. You can see the frequency for the transponder, the linear transponder. AO7 and AO27 still chugging along with some time constraints. And this picture, by the way, is the Dwinglo in the Netherlands PyCam radio telescope, which has been invaluable for receiving weak signals. They've been so wonderful to us, particularly receiving AO109, which has recently re-entered. But in the meantime, we got lots of telemetry from them. And you know about the ISS, I expect. I think you recently had some ISS contacts. but they do have a repeater that runs frequently, an APRS digipeater. And right now, again, I think you're aware of this, they are doing downlink of some slow scan TV signals. And occasionally, instead of a repeater, you'll find a live astronaut. That actually happened to me once. I was totally shocked. And I got a nice QSL card from them. So thank you for listening. I think you can see that a lot's going on in AMSAT-NA. Hopefully will yield exciting results over the next few years. And in the meantime, there are several satellites AMSAT developed that are operational, not to mention a number from AMSAT UK and other organizations, including ARIS on the ISS. So thanks for listening. And do we have time for any questions, Ian, or we're kind of at the end? I know I went over a little bit.
Hi there, it's Barry here. We've got a few minutes for a couple of questions. If anybody has any questions. Any questions? No, I think that was actually a fantastic presentation, Burns. That was brilliant. It tells us what's going on in the States. So could we all show our appreciation, please, in the usual way?
Okay, very good.
Thank you very much indeed for bringing us up to the date on what's happening in AMSAT-NA. It's much appreciated.
Well, sure, and thanks for having me. I enjoyed it.
Thank you very much.
Okay, so long.
Cheers. Hand over to you, Ian.
Okay. Thank you everybody for staying late. I know we ran a little over time. This formally ends the Colloquium program. So all that remains for me to do is to say thank you to everybody for coming. Thank you to the BATC for providing the web stream. Thank you for the RSGB for hosting us. Thank you for Kent Hill providing the venue. And as I say, thank you all for coming. Have a safe trip home, and hopefully we'll see you all next year.